I just introduced myself. Okay. Yesterday I promised two constructions of four manifolds, and I gave you one with the knot surgery, and it already produced, in many cases, infinitely many distinct smooth structures. I will recall another one, and we will apply it in another situation. But before doing that, let me just remind you a very simple construction, and this will be familiar for most of you, but I like it so much, so I will just go through that. So let's take the following space. This is will be familiar. This is the tautological line bundle. So we take pairs P and L, where P is a point in C2, and L is a line in C2 passing through the origin. So it's a point in the projective line under the condition that P is in L. So this is the same as we take pairs of points, say the coordinates in C are xy, and the homogeneous coordinates in CP1 are u and v. And this condition means that the slope of the line passing through xy should be the same as the slope uv. So the condition is x over y should be equal to u over v. This is a little bit sort of undefined when y or v are 0. So instead, we just say that xv should be equal to uy. So this is a 3 complex dimensional object, and we just have one condition. So this is a 2 complex dimensional, real 4-dimensional thing inside that product. And notice it has 2 projections. The first is when we project down to the first coordinate C2, and the other one is when we project to CP1. So what are the fibers of these projections? Well, if we pick this just maps the pair point line to the line, and we just encounter in the inverse image all points which are on that particular line. So this is a line bundle. And indeed, this is the tautological line bundle. But when we project to this factor, so we associate to PL the point P, then typically we have the inverse image, or the fiber of this map, is only one point, because there is only one line which passes through my point and the origin. With one exception, when my point is exactly the origin, then there is a whole CP1 worth of lines, because all the lines qualify. So this is a map which is 1-to-1, except over the origin, where the inverse image is just a CP1. And this map is called the blow-up map, and you might understand why is it blow up. You just take C2, and instead of the origin, you just blow some air into that point, and then it becomes a sphere. Okay? If you like this picture, but you would like to play a little more with it, try the real version. And what you get is, in fact, the Möbius band, which is also a line bundle over RP1, which is just, you go around and then you have to make one twist. That's a tautological real line bundle. But if you view the Möbius band sort of sideways, then you see how the lines turn. And of course, when it comes back to the original position, then it has to sort of glue up. So you don't see the projection so well, but using your imagination, you can do that. So this is a very important construction in low-dimensional topology. And in fact, this space is some well-known object. You just take CP2 minus a point, and you will see a diffeomorphism. I mean, you have to convince yourself about that. I will not argue. If you also consider this as an oriented object, it's a complex subspace of a complex manifold, so it comes with a natural orientation. Then, in fact, you have to take the opposite to the natural orientation of CP2. Okay, so the lesson we have to learn from this story is that somehow when you see a 4-manifold and there is a -1 sphere, so like the generator, the complex projective line in CP2 bar, then you can collapse that -1 sphere into a point, and you still get a smooth manifold. So that's what's called the blow-down procedure. Whenever you have a four-manifold, collapse the -1 sphere to a point, and you have another smooth four-manifold. And then you might become, a little more greedy, and you would like to collapse other curves or two-dimensional subspaces in four-manifolds, and this is what the rational blowdown is about. So maybe I will just erase it from here. And rational blowdown. So the idea is the same. Consider a configuration of curves of two-dimensional spheres in a four-manifold X and collapse them. So consider the quotient topology where all the points on these spheres become one point and otherwise, why is that? Is it too loud or is it okay? I'm not singing, so it's okay. Yeah. So we have this X and we have some spheres. For simplicity, I will assume that they form a connected subset. So sphere 1, sphere 2, sphere 3, and then we collapse it to a point. And what we get is typically a singular object. There is some kind of singularity, which is, the singularity is just a cone on the boundary of the tubular neighborhood of this configuration. And what we would like to do is to erase this. Well, in this construction, we took the tubular neighborhood of a -1 sphere and we replaced it by a disk. Well, we cannot do that because we don't know whether this boundary is S3 or not, or something else. Typically something else. And we would like to glue in, well, we cannot do it with the disk, so we plan to do it with a rational disk. Rational disk means that we take this four-manifold with boundary, which has the same rational homology as the disk. So up to rational homology is the disk, otherwise it's a little more complicated. The question is, when can we do that? And here are some examples. So the aim, glue in a rational homology for disk. So erase this guy and glue in a QHD4. So that's the plan. And of course, our hope is that we find interesting configurations such that when we do this operation, then we will get exotica. We will get manifolds which are homeomorphic to something standard, but not diffeomorphic. And this is exactly what will happen. So here is a fact, or rather a construction. So consider CP2 bar. So just the complex projective plane with the opposite orientation. As usual, this potato is supposed to symbolize that. And we take a degree 2 curve. Degree 2 is symbolized by this parabola, right? So it's a sphere inside CP2 with self-intersection -4. So sphere of self-intersection -4. Okay. Now notice that if we take the tubular neighborhood out, what's left, we'll have no rational homology, the rational second homology. The second homology of CP2 bar is the same as for CP2, which is isomorphic to Z, and we take twice the generator out. So nothing remains, only some torsion element. So when we take rational homology, the second homology of CP2 bar minus this sphere C will be 0. So this is a fantastic candidate. So that just tells us that if you have a -4 sphere, then we can just run this algorithm and we replace it with something. Well, it will not be a disk and it will have some fundamental groups. So we might vary a little bit what happens with the when we glue this in, maybe we will create fundamental group, maybe we change the homeomorphism type, so we have to be careful. But this single example gives us a whole family of similar examples, because now I take, instead of the degree 2 curve, I take a line which will intersect it in 2 points. Well, I'm working in CP2 bar, so the 2 intersections are both negative, but I can make a little trick. I take this line and I equip it with the opposite orientation. So this is the degree 2 curve with the usual, and this is the line with the opposite orientation. So I have 2 positive intersection points. And now I start the game. I can always, so the self-intersection of this is -4, and this is -1. And I can start blowing up. I always blow up either this point or that point. So the next configuration will look like, so say we blow up this point, it will look like this. And these self-intersections change. Under blow up, it always drops by 1, and the pairwise intersection sort of disappears. So this is a -5, this is -2, -1. And now I take the tubular neighborhood of these 2 curves, and I run the same argument. Now, when we blow up, as I tried to convince you, we just take a connected sum with CP2 bar. So now the second homology of this whole 4 manifold is Z plus Z. And now I take out the tubular neighborhood of 2 surfaces. So what's left, again, we'll have second homology measured with rational coefficients to be 0. And I just keep repeating this game, and I get a complicated family. I always have a choice which point to blow up. In the first step, it doesn't matter. You will get the same configuration. But for example, here, you can blow up either this point or that point and just keep doing that. So it's a little exercise that at the end of the day, by doing it n times, you get a configuration of spheres which intersect each other along a chain with self-intersections A1, A2 up to AN. And if you take the continued fraction base formed from these numbers, so this number, the continued fraction of A1 up to AN, which is equal to A1 minus 1 over A2 minus 1 over A3, and so on. This will be equal to a rational number of this type, P squared over PQ minus 1, PQ relatively prime. It's not so important, but this story works both ways. If you get a rational number of this type, you take the continued fraction expansion, you have the corresponding plumbing, and you can create it in this way. So I gave you a lot of examples of configurations we should look for, and a lot of rational homology disk we can sort of apply this construction with. I will only use it for the first one when we have a -5 and a -2. Okay, so far so good. Of course, you can consider other configurations of curves, maybe not only spheres, but which intersect each other along a more complicated plumbing graph. And there are results along those lines, but let's stick to the original one. I should add the usual 2 names, Fintushal and Stern, who sort of first used this construction to create interesting 4 manifolds. Okay, so where do we use this construction? So let me start with a remark. So suppose that X is a negative definite 4 manifold. This just means that QX is negative definite. by the combination of Donaldson's diagonalizability theorem and the Friedman classification, provided that X is simply connected, we get that X is homeomorphic to some number of copies of CP2 bar. We also allow the degenerate case when n equals 0, then I just consider it to be S4, and other than that, you have CP2 bar or two CP2 bars connected sound, and so on. So this is an infinite family of four manifolds, and you know, this family contains our most interesting example of S4 when we are asking whether they support any exotic structures. And then the answer, we don't know. So no example so far of exotics on these examples. So let's relax one of these conditions, and I pick this one. So what if we relax this condition and we substitute it with pi1, not to be trivial, but the group of two elements, so the next level. And surprisingly, we have a much better result. And this is what I would like to talk a little bit about. So here is the theorem, which we proved last year with Zoltán, or maybe 2 years ago. So suppose that X is a topological four manifold with fundamental group Z2 if X admits a smooth structure. So this just says that Donaldson's, with negative definite intersection form. So this is exactly the same situation, except I allow, or I demand the fundamental group be a little bit bigger. And then the statement is that if X admits a smooth structure, and there is an annoying assumption that the second Betti number is positive, then X admits infinitely many distinct smooth structures. So this family is very similar to this one, except you will see I will give the topological description. And the theorem holds for each and every one of these family except for the very first one, which is very similar to somehow the S4 in this family. So, you know. Okay, so let me give you a construction of four manifolds with Z2 fundamental group. This is a very simple construction. So let's take A to be the antipodal map. So this just sends X to minus X, right? So you take the sphere and then you just map it to the opposite. And let's take C to be complex conjugation, where now S2 is viewed as CP1, which is just C2 union the infinity. Okay, so these are two involutions on S2. This is a fixed point free involution. This guy has a fixed point set. It's a circle, the real line or the real circle. Okay, so this and both are orientation reversing. So now consider L2 to be S2 cross S2 divided by, and what's the convention we followed? A cross C and L2 tilde to be S2 cross S2 divided by A cross A. So these are two four manifolds, S2 cross S2, and we have two involutions. In the first one, I apply the antipodal on the first coordinate and the complex conjugation on the second at the same time. So this is an order 2 self-diffeomorphism. Since A has no fixed points, this map doesn't have a fixed point, so it's a fixed point free action of Z2. This is orientation reversing, and this is orientation reversing. So if you put them next to each other, they suddenly become orientation preserving. So what you get is a four manifold, which is the double cover of it is S2 cross S2, which is simply connected. So pi 1 of this guy is Z2 oriented, smooth four manifold. Likewise, this one. It needs a little bit of a thinking that this construction will give a spin example, and this is non-spin. And indeed, if you work a little bit with this construction, you will realize that both are S2 bundles over RP2. So these are the two S2 bundles over RP2. So they resemble two S2 bundles over S2. If we have two of those, there is the product, which is S2 cross S2, and there is the non-trivial one, which is a CP2 blown up once. And they are sort of similar to that. One of them is spin, the other one is non-spin. The similarity even holds that if you blow up one of them, then it will become the same as the blow up of the other. So these are diffeomorphic. So it's very similar to the simply connected case when you take S2 bundles over S2. Now we take S2 bundles over RP2. So we pick up a little bit of a fundamental group, but everything is exactly the same. And indeed, if we have a topological four manifold with negative definite intersection form, if this happens to be smooth, as we assume, then by Donaldson's theorem, the intersection form has to be diagonalizable. We assume that it's negative definite. So such X is homeomorphic to L2 connected some number of CP2 bars, or L2 tilde connected some n times CP2 bar. Provided n is at least 1, it doesn't matter. And notice that I assumed this little assumption, which just sort of excludes the discussion about L2 and L2 tilde. It's easy to see that B2 of L2 as well as B2 of L2 tilde is just 0. So we take all the negative definite four manifolds which have a chance to have a smooth structure, or they do at least one, and we exclude these two very little ones. They are just too small for our considerations. And then the statement is that they all admit infinitely many structures. So it's sort of one step forward to show that it's not completely crazy to assume that if a four manifold has a smooth structure, then it will have infinitely many. As I mentioned, we don't have any example which would contradict this statement, and we are gathering more and more evidence which supports that expectation. I wouldn't say that it's a conjecture, because that's too much, but you know. Okay, so say it again. You have to wait. You have to sort of grow up to it, and you ripe a little bit. You know, every math lecture should come with a proof and a joke, and hopefully the two are sort of distinct. And so I will not give the proof of this statement. I will give one special case. So let's argue. So argue for B2 x equals 4 i.e. when X is L2 connected some 4 times CP2 bar. This is sort of the easiest to formulate, and I will present you the proof for this case, and then a little modification can be applied when B2 is bigger than 4, and when it's smaller, there are only 3 cases, then you have to suffer a little more. Okay. Before going any further, notice that B2 plus of such a manifold is 0, which means that the usual Seiberg-Witten invariants are all 0. You remember yesterday we agreed that if B1 is 0, which is 0 now because it's a torsion group, pi 1 is a torsion, then in order to have sensible Seiberg-Witten invariants, numerical Seiberg-Witten invariants, you need B2 plus to be odd. And now it's 0. So Seiberg-Witten of X is constant 0. So there is no real hope on the nose to apply this theory and to distinguish the smooth structures. But there is a very simple trick, which I will just outline in the corner of the blackboard. So suppose X1 and X2 are manifolds of this type. So they have a little fundamental group. They have fundamental group Z2. And suppose there is a diffeomorphism. Whenever you have a manifold with fundamental group, the first thing you should do is to take the universal cover, which happens to be a double cover in this case. So we just take the double covers. And of course, then you can compose this map, and you have a map from X1 tilde to X2, but you know when to lift a map. You know, that is described provided you understand how the fundamental groups map. So there is a map up to capital F. And it's easy to see that if F is a diffeomorphism, then capital F will be also a diffeomorphism. So if you can obstruct the existence of capital F, then you obstruct the existence of little f. And now we should see what happens with the invariants of these X tildes. And in fact, for all X of the theorem, B2 plus of X tilde is odd. I advise you to do it once. It's very simple, and it relates and it relies on the fact that when you take a double cover, the Euler characteristic multiplies by 2, and so does the signature, but not B0 and not B4. So this is where this sort of the shift between being 0 and becoming odd happens. Just check it. So the message is that that Seiberg-Witten theory will tell you very little down here, but it will tell you a lot up there. Of course, you can phrase everything in terms of real Seiberg-Witten theory, but now I'm sticking to the version I was referring to yesterday. Okay? So the plan is the following. When we would like to construct exotica in this category of 4 manifolds, we better turn to simply connected guys and try to find exotic simply connected examples equipped with an orientation-preserving free involution. This is what we need, okay? And this is exactly what we will do. Okay. So look for exotic examples, exotic simply connected examples with orientation-preserving free involutions. Before going any further, let's do the sort of, I'm not doing it, but let's see what is the double cover of this manifold. So if you have something which is homeomorphic to L2 connected some 4CP2 bar, well, then X tilde, it's not hard to compute. because we know what is the universal cover of L2. This was just the Z2 factor of S2 cross S2. And this is a simply connected piece, so it will appear twice. So we have to take an 8-fold connected sum. And well, this requires only a little yoga to realize that this manifold is the same as CP2 connected sum 9 CP2 bars. So when I promise an argument for this special case, what I really have to do is to consider this 4-manifold, this topological 4-manifold, and equip it with infinitely many smooth structures, all coming with an orientation-preserving free involution. And this is exactly what I would like to do. Okay. Here? Yeah, but it's easier than that. I mean, Kirby calculus is easy, but this is easier. You can discuss that. It's a very simple construction of taking the trivial bundle, trivial S2 bundle over S2, and blow up one point, and then instead of blowing that -1 sphere back, you blow down the X fiber. And then you go from S2 cross S2 to CP2 blown up 1 point. So this is true even if it's not 8, but 1, and then it will become 2. Okay? Okay. Let's see. So we consider S2 cross S2, and I consider the involution iota, which is just A cross A, the two antipodal maps. Okay? So unfortunately, I have these schematics. For me, S2 cross S2 is always like a box. So not of chocolate, it's just a box. S2 cross S2, there are the horizontal and the vertical S2s. And now I take two curves in it, and we will consider the pencil generated by these two curves. So let's take C0 to be two horizontal and two vertical lines. So this is like S2 cross A union S2 cross B union C cross S2 union D cross S2. And the only assumption is, I see, maybe XY. And the only assumption I have for these chosen four curves is that the corresponding XY and the CD are not images of each other under the antipodal map. So they are not just opposite points. Other than that, we have complete freedom. And so this is C0. And then C1 should be the image under the involution. So this is something like this. Okay? So we have two curves representing the same homology class. So they are zero sets of two sections of the same line bundle. So we can sort of take a line across these two sections. Said differently, we can consider the pencil generated by these two complex curves on S2 cross S2. So consider the pencil on S2 cross S2 generated by C0 and C1. Well, we discussed that, or it has been discussed yesterday, that if you have a pencil, then there are the points which are on each and every one of the curves, namely the intersection points of C0 and C1. There are exactly 8 of them, right? I will just circle them. And they come in pairs. The involution just swaps them, right? So with 8 base points, 4 pairs swapped by iota. Right? So each pair has 2 points where iota just sort of flips them. So if I blow up 1 point, then I don't know how to extend my involution to that. But if I blow up both points in a pair, then the involution will sort of swap the -1 spheres, which I introduced during this blow up. So the iota will extend to the blow up if I do all of them. Or actually, it will extend to the intermediate stages, provided I always do these equivariant blow-ups. I blow up both points in a pair. So blow up the base points. Then get a iota, the same letter, on S2 cross S2 blown up in 8 points. Okay. Of course, if I take the quotient, then I will just get back my target manifold. So this is, again, an orientation preserving free Z2 action on that particular smooth 4 manifold, right? But we also notice that if we have a pencil of curves and we blow up all the base points, then we do get a fibration. So this comes with a fibration after blow up. Get fibration on S2 cross S2, which maps into CP1. This is the perimeter space of the curves in the pencil. They are parameterized by a rational point, a point on the complex line. And so it's a fibration in a more general setting. It's not a true locally trivial fibration. It is called an elliptic fibration. Somehow you might guess what the fiber should be. These 4 lines give you a singular curve. It has 4 singular points, exactly the ones on the intersection points. So this one, this one, this one, and this one. If we smooth those points, then you will see a torus inside. Well, it's a weak argument, but this is something what happens that generically in this pencil, the general curve will be a torus, an elliptic curve. This is why it's an elliptic fibration. And clearly it has to have singular points, because if you have a torus fibration on any manifold, then the Euler characteristic, it multiplies, so it will be always 0. But we clearly see that this is a simply connected 4 manifold with huge second homology. The Euler characteristic is not 0. Nevertheless, it turns out that it will have several singular fibers, which we can sort of understand, and I will just pick 2 of those. So now this box is supposed to indicate this 4 manifold, together with a map into CP1. There are 2 singular fibers which we should see immediately, the blue and the orange. They are somewhere. They map to some point. And there are further singular fibers, and I claim that there are at least 2 fishtail fibers. So, fishtails. So a fishtail fiber is just an S2 with a double point. So we take a regular S2, and we take 2 points, and we identify those 2 points. So it's a nodal curve. There are 2 such that the involution just swaps them. Similarly, every blow-up will provide a sectional depth of that fibration. A blow-up will intersect each and every curve in the pencil, and we take 2 of those which belong to a pair here. So the iota will not only swap the 2 fishtail fibers, but it will also swap these guys. A fiber has self-intersection 0. The sections are all -1 curves, -1 spheres. So let me sort of extract the important thing from that picture. So we have.
How to define a map to CP1?
Say it again.
What's the map? How to define a map to CP1?
So it is defined by the pencil. So the pencil looks like that it covers the entire S2 cross S2 one-fold, except the 8 points infinitely many times, right? So it looks like this in these points. Every curve passes through, but they come from different directions. Other than that, every point is covered only once. So when you pick a point, there is only one curve in this family which passes through that, and that curve is given by a projective parameter, and you send this point to that particular projective parameter. It's a fun little construction, and it's much easier to understand in CP2 when you take two lines, and everybody behaves nicely. It's really once covered, except this point infinitely many times, but when you blow up, then this infinite sort of goes all around the CP1. And we do that with more fancier curves, but the principle is exactly the same. Okay, so this is my picture now. And we are still in that four manifold. And now what we will do, we will apply four more blow-ups. We blow up these double points, and we blow up these 2 points. Notice that these are, again, we can do it in an equivariant fashion because the two curves map to each other under iota, so their singular points should map into each other, and these sections map into each other, so these 2 points should map to each other. When we blow them up, what we get is that this double point will sort of smooth out. It will become a smooth curve. So we have -1, -1. So we have this curve becomes a -5 sphere, because when you blow up the double point, it drops the self-intersection by 4. I will not argue why, but it's not very complicated. And we blow it up one more time. There is a -1, the blow up here. This guy will become a -2, because it used to be a -1. There is another -5, a -1, and -2. So miraculously, we see 2 copies of this -5, -2 I was referring to earlier. Here is one, and there is another one. They are disjoint. They map into each other under the involution. So we can use this rational blowdown construction. Notice that we changed our four manifold. We started with that, and we blew up 4 more times, but now we sort of take it back rationally. We take 4 homology elements away, and we replace it with something which doesn't bring any new homology. And we do that, and we get a new 4 manifold upstairs, but with an involution. So let me just erase this. Two rational blowdowns. And we get, I don't know, x 2, 5. And now comes a little yoga. Now we have to understand the signature, the Euler characteristic, the parity, apply Friedman's theorem that this is homeomorphic to S2 cross S2 connected sum 8 times CP2 bar. It admits an involution, but not diffeomorphic to S2 cross S2 blown up 8 times. And again, this line can be verified using Seiberg-Witten theory because now we are in the upstairs regime where the B2 plus invariant is in place and everything is nice. So consequently, when we factor out with the involution, we get an exotic structure downstairs which was a homeomorphic to this L2 connected sum 4 CP2 bar. And then, you conjugate this idea a little more. You you do more blow-ups, and you get other examples of this family, which I was referring to, this p square over pq minus 1, and you get an infinite family of using the same strategy. And you always use the same amount of blow-ups as much you blow down. You never change the homeomorphism type, but you always change the diffeomorphism type, and that's the end of the story. So you can, sometimes when Cyber-Witten theory refuses to help you, you can sort of make a little covering, or you do real Cyber-Witten, or you do some kind of a trick, and then it will help you again. Not always. There will be a limit when it will not help you, and you have to find out something else. So this was sort of a construction of 4 manifolds, and then starting tomorrow, Zoltán will give you further ways of presenting and constructing 4 manifolds and understanding them using something very similar to what I was talking about here, using fibration structures, so how to make 4 manifolds in a more trickier way out of 2-dimensional pieces, but you have to sleep one more time until you get there, okay? Yes?
Does this mean that you have here an exotic involution on this contact connected to
I mean, so we have an other smooth structure. So it's
standard smooth structure.
no. It's not the standard smooth structure. It's it's the standard topological manifold with a strange.
The topological involution on the standard structure.
Exactly. You can phrase it like that, yeah. Or it's a standard involution for an exotic diffeomorphism type, yes. Although there is no standard anymore. When it's exotic, there is no standardness. I'm not saying that we lose all our standards, but yeah. And then you can do it for other manifolds. There is a whole bunch of other manifolds you can do the same trick.
How many blow-ups did you do here? 8?
Here, yeah, I circled them. These are exactly 8 because.
Okay. So you do 8 blow-ups, then you do 2 rational blowdowns. Why do you still get 8 copies?
Okay, so let's accounting. That's very important. So we do 8 blow-ups. We end up here. Then I proposed 4 more. Here are the circles. In order to create this configuration, you do 4 more.
Oh, okay.
And then you take back those 4 more by 2 and 2. I swear, math works. It's magic. Yeah, and then you can do more blow-ups, but you find longer and longer chains, and they sort of come in pairs, and they balance. You have to be a little careful how to blow up, because at the end of the day, in order to have this homeomorphism type, it's not enough to count Euler characteristic signature and parity, but you have to make sure that what you get is simply connected. And what you replace your simply connected configuration with is not simply connected. And indeed, its non-simple connectivity will pump up the Cyber-Witten values. So somehow, that's exactly what Cyber-Witten theory measures in principle, that locally you have some fundamental group when you replace the simply connected one with non-simply connected, but globally it will not affect the fundamental group. So that's somehow the magic. So, you have to value local fundamental groups. That's the lesson. If there are no other questions, then we are free to go and have lunch.